Today we are going to look at machine learning training. Over the last 2 or 3 days, the last 2 or 3 classes from last week and this week, we have looked at history of machine learning. We have looked at the different methods of machine learning. We have looked at the steps, when we talk about training cycle or training process, right? We've looked at the steps as well. So today we are going to start digging into the actual thing. Of course, right now we have a task that has been placed, and we are talking about linear regression. So it is my hope that today we should be able to get to a point where everyone will understand what linear regression is and how you can do it. So we are going to look at the machine learning life cycle again quickly. We'll just run through it and try to, um, you know, get an understanding of the process. This is more or less the same as what we have done before. So I'm not going to dwell on it too much. So remember, the life cycle starts with data collection. You collect raw data wherever that data comes from, whether it's from sensors, from databases, APIs, user input, and all, manner of places, right? So it is really key that the data is of high quality, garbage in, garbage out, right? Now, this is a terminology or a jargon, how do I put it? A slogan that we use a lot in, computer science and so on. And it used to be used in the days of programming. But you can see that it is even more applicable now when we are talking machine learning. If you give your machine learning model, garbage data, it is also going to give you garbage as, output, right? It's not going to be intelligence. So be very careful. There's a kind of thing that says, the anyway, I'll look at that in the subsequent slides. But really, the data that you bring in has the highest impact on your model more than anything else. So data preparation, after you collect the data, you need to prepare it. Data is not always perfect. So you have to clean it, you have to transform it. So today we are going to look at that a little bit. We're going to do what we call normalization, encoding, splitting data. And then the typical test train split, which is 70% for training data, 15% for validation, and 15% for test data. Then you now go into model training, which is the real deal. When we talk about machine learning, we always kind of focus on the training, right? But yeah, it's not only about the training, but training is like the core of it, is at the center of it. And you have to first of all pick what type of model architecture, right? Um, you have to pick the the architecture, right? And you have to pick hyperparameters and other things. Okay. Then after that, you go ahead into doing the training. Training basically is the process of minimizing the loss function. The loss function or the cost function is a measure of how far away the model is from what you want it to be able to do, or from what you want it to be able to predict. So if your model is very far away, then the loss function will be very high. But if the model is very close to what you want it to predict, then the loss function will be very low. So it's an optimization problem, basically. Um, then you do model evaluation as part of the training cycle. You do the model evaluation. After the model evaluation, you do you compare. Typically, you use model evaluation to uh, when you are doing architecture search or model search, you are trying to choose or design which one is the best type of model for you to use, right? So you would typically go and compare models, you measure how they perform on the same validation data set. Okay. And once you are able to define a constant set of metrics, then that is what you will use to differentiate the models. The model deployment, right? Model deployment is where you put it up there, out there in the cloud, okay, so that others can make use of it. And then model maintenance and retraining. So maintenance and retraining is very important because your model will get old. The data that you train it on will get outdated. So if you don't want your model to, become irrelevant or useless, you will have to um, continue to improve it, to refresh it, to retrain it. So if you train it on some data and new data has come in, you need to collect the new data as well, maybe combine it with the old data, right? So that you don't have a huge drop, okay, in the model's performance um, or large gradients. Because if you take new data and you don't mix in old data, you may have very large gradients that could damage the model. So you mix it up, but basically it just means you add more additional data that you use to retrain the model so that the model becomes updated. Of course, while you are retraining the model, you have a copy of it running in production. It's not the one that's running in production that you will retrain. You retrain a copy of it. And when it's all done, you redeploy that. So that's the continuous improvement phase of the machine learning lifecycle. So we are going to just quickly go through this. Data processing. What are the things that you can do during data processing, right? You you can transform, right? Organize raw data into a usable format. Okay. The data is not perfect, like I've said. It can be, it can have missing values. So for example, if you collected data um, on students, some may provide you age, gender, some may not. So for those data points or records that don't provide you this information, what do you do? How do you handle it? So that is where handling missing values comes in. You have to have a strategy when you are handling missing values. You have to decide, how do I address for each field or for each feature, you have to have a plan of how you handle missing values. Then there is categorical data. Categorical data is data that is not numeric in nature. Of course, in most cases, the data that you are training on are not numeric, right? The data is made up of different things. Images, for example, even though the representation of images is numeric, it's images are represented as a bunch of numbers, okay? Structured in a specific way, maybe where they represent the pixels or the color values and the color intensities. So that is how images are represented. Text, words, right? So there are other things, sound, for example, and so on. So in all of this, you have to convert the data from its native format, right, to a numerical representation. And there is categorical data. Categorical data is basically features that are not actually numeric, but they represent a classification or a categorization of things. So you have to figure out how to encode it. And there are many different ways of encoding, which we are going to talk about later on as well. Then you do feature scaling, right? You remove outliers. Feature scaling is if you have, after you have done encoding, where you convert every feature into numerical values, you may find that some of the numbers or the values may be so high, they will be out of range. They may give the computational engines or the computing engines, the CPU, GPU, and TPUs, some kind of difficulty because of numeric limits. So you sometimes scale them. The other thing they would cause is what we call gradient explosion, right? Exploding gradients and diminishing gradients. These are all challenges that you face when you're training models. So in order for you to not have those kind of issues, you would do feature scaling. Okay. Then removing outliers. Perhaps there are some values that are too far away from the mean distribution or from the center of the distribution of data. So then feature selection or extraction. So these are some of the things you could do. So data cleaning is that process of identifying and correcting errors or inconsistencies in the data set. You do this because you want to improve the quality of the data set, because the raw data set may contain a lot of inconsistencies. Some may even just be wrong data. Some may be noise. Some may be duplicates, missing values, and so on. So you have to clean your data set. And typically, some of the things you would do, like I've already mentioned, is there are some features or columns that are irrelevant. So you drop those ones. For example, serial number. If you have a data set and then you have serial number or ID number, right? There's no real correlation between the serial number and what you want to, predict or get out of that data. So you may drop that, or ID identification numbers. Okay. The other thing is you want to ensure data consistency. You want to also resolve missing values. Like I said, there are strategies. You either can decide to replace, right, with same values from the mean of the distribution or median of the distribution or some other approach. Or you can just remove those missing values completely. Duplicate records are removed, and so on and so forth. So all of this basically are the things that you would do when you are doing pre-processing. Some of the tools that you can use for data pre-processing. I mentioned a few tools last Monday. Pandas is a really good tool. Pandas allows you to clean your data set. It has a bunch of functions like this filter, drop duplicates that can remove duplicates, and then drop now, which can remove the empty or missing values, right? And then duplicated is a function that allows you to see which rows are duplicates, right? And then rename also allows you to rename columns so that they can be more meaningful. So these are some of the things you can do with pandas. So what I'm going to do is I will take us through just a really quick hands-on how you can do data preprocessing. Now, because this is not really a course on data preprocessing, I will not be able to show you everything. Um, but I will, you will still have to do a bit of work on your own in order to really have a good grasp for it, because there is so much for us to do. It will really be difficult. So let's try out a few things. So I'm going to start off with I'm going to use a Jupyter notebook, and I'm going to pull in some data from Kaggle. So this is a data set that, may have some kind of, you know, um, incomplete data, missing rows, and so on. And then we are going to look at how to use pandas to do it. So share my screen. Okay, so we start first of all, we're going to go to Kaggle, and I'll show you a simple search for Um, Data cleaning, example, data sets. Right. Now, there are a lot of people that have all of this. I think it's better to search under data sets. Um, okay, there's a particular data set I'm looking for. But right, so this is a data set. If you look at this, you will see um, this is text cleaning data set that has um, emojis. It has exclamation. It has a whole bunch of um, characters here. So now these are some of the things that you would use. You know, if you want to use this for training a model like a neural network or text model, you could use that. But this is not the one that I would want us to use. So I'm going to um, specific data set that I am looking for. Uh, Okay, sorry for the short outage. Right. So, this data set contains numerical values. The reason why I really wanted this data set was I wanted the one that is numerical values so that it will be simpler to understand what we are doing when we are, you know, doing the data cleaning. So, give me a thumbs up if you can hear me still. Okay. All right. So, if you look at this data set, you see that there are you see that there are number of on this column, for example, you have a rank column, you have a peak column, you have all-time peak, you have actual gross, adjusted gross, um, you have artist, store title, years, shows, average gross. So this data set is a data set that was pulled from a Wikipedia page. If you go to the top here where you see the description, it was scraped from a Wikipedia page, right? And you can even see the code. They have even given a link to the code that was used to do the web scraping. So typically, when you pull data from the web using web scraping like this, you will see that there is a lot of the data is not going to be clean. There's a lot of um, you know uh, junk, basically, if I may use that terminology, right, in the data. So you need to clean it up. In this particular data set, because of the nature of the code that was used to scrape this data, you see that columns like peak, right, has no value here, right? It has 55% of the values in this row or in this column rather. 55% of them are null, right? 10% of them have a value of 1. 55% of them have value, other values. All-time peak, 70% of the values are null. So these are missing values when we talk about missing values. Then 5% of them are, have the value 2 and so on. Here, all you have duplicates, you have 20 unique value. But when you look at this column, you see that it's actual gross, it's actual, it's numbers, it's currency, right? It's amount. So it's okay to have duplicates. They are just a gross as well. So this has to do with how much different artists are earning. So you see the artist name here as well. So you see Taylor Swift, Madonna, and others. And there's also duplicates. There's repetition based on the tours. So this is the tours that they took. You see uh, the title of the tour, right? The year that the tour was done, the number of shows in that tour. So if you wanted to do a bit of data cleaning on this, right, you are going to look at all of this and you ask yourself, what do I even want to do first? Maybe I want to do a regression model. So again, it depends on the problem. Let's assume that the problem was want you to do a regression model to predict how much, maybe if Taylor Swift were to go on a tour in 2026, you know, how much do you think the person will make, you know, or something like that. So to clean this, there are several things you would have to do. The first one would be you cannot do anything with all of these null values. So you need to ask yourself, what do I do with a column, right, that has so many null values? You can fill in the null values, the blanks, right, here, but what will you fill it with, right? So this is the thing with data pre-processing is you have to first of all ask yourself questions. You have to come up with a strategy. So it's not really about the coding itself. The coding is easy. You can actually even use AI to generate the code. But the question is, what is the best strategy to use? This column here is peak. What does peak mean? Okay, what does peak mean? What does it refer to? Maybe it is the peak um, ranking or rating of in that store. So you have 1 1. You can see there are duplicates as well, 1 1 2 2 2 2, and so on. Right. And then you have these other things in bracket. What are these things in bracket? So if you go to check the source of this data on the Wikipedia page, which you can go there to check. You can actually, if you go to this, you will see where that refers to. But if you go there to check, you find that these numbers here in square brackets are references. You know how, like in a Wikipedia page, you have numbers in bracket that are references. You click on that link on that reference to get more information. So somehow the references got pulled in along with the actual data. So for this column, if you want to use this column or this feature, you would have to first of all remove the references. But the question is, why do you even want to use this column? What does this column do for you? What value is it to the model that you want to train? This is another column, all-time peak. So this is peak and this is all-time peak. All right. So then you have another column, the actual gross. So this is the actual amount of money that was earned in that particular tour, right? The adjusted gross is adjusted for something. I don't know what it's adjusted for. Maybe um, additional, earnings that came later, that were not in that range. Then this is the name of the artist. Of course, an artist can go for multiple tours. So you see that it's not a unique field. Then the tour title, then the year, the number of shows. So for me, I would ask the ranking. This rank is when you look at rank, what is it? What does it even mean? Is it like the ranking of the the you know that particular tour? So it's the ranking. So a ranking of 1 means that's the highest, the one with the highest revenue. Okay, $780 million. Number 2, ranking 579. So the ranking also is a useful field. The interesting thing is if you look at this ranking, you see here that this number 7 is repeated, right? Was there a tie? You see there wasn't a tie here. If this is what is being used to rank, there's not a tie. So this might be a typo. So this is another case where you say, okay, I know what this means. So in cleaning this particular column, I will want to replace it with what it actually stands for. So this is what I'm doing right now is what we call exploratory data analysis. You're just looking at the data. You may not look at all the data, right? Now, the interesting thing here is that Kaggle already has this thing displayed for us, so we can easily do the exploratory data analysis just by looking at this. And Kaggle also gives additional capabilities. So for example, you can check a compact. This is a compact way of looking at it. This is a column way. This one is really nice because this one allows you, for each column, you can see statistics on the column. The numbers that are valid, the numbers that are missing, the percentages. And then you can see the numerical statistics. Mean is 10.4, standard deviation, and quantities. This is kind of bucketing. So remember, we were talking about bucketing for categorization. So you have mean 25%, percentiles basically, how many fall in each of these percentiles. But for a column like rank, all of this doesn't make sense. Okay. There's also a graph here, by the way. This is a bar graph. But for a column like rank, it doesn't really make sense. It's just an ordering. So I will not even bother about that for rank. But you can look at a column that makes sense to do the statistics. For example, the actual gross, right? So you can see the most common is 780,000, 5% of the time. Valid, 100% of the values are valid. There are 20 unique values. Um, and um, how many rows are there? That's something um, Well, I assume there are 20 rows, but then there are 20 unique values. So, so this allows you to take a deeper look at statistics of each column. So Kaggle already gives you this. But if you didn't have Kaggle, you could still do it yourself. So let's start off with simple Jupyter Notebook. Um, Collab.new is going to create a new notebook. Okay. Then while that is going on, I'll show you an easy way you can load data from Kaggle directly in your notebook instead of downloading and re-uploading it. First thing you do is copy this link here, right? That actually points to the data set. And when you copy it, also take note of this data explorer that is telling you you have a myfile1.csv. So take note of this. You have one file in the folder, right? You have one CSV file. That's a summary. But take note of the file name. This is the file name that you will use. So the first thing is we need to import Kaggle Hub. Kaggle Hub comes with Collab, so you don't need to install it. But typically, if it wasn't there, you would have to do pip install to install it. But Kaggle Hub is there. So now, for you to load the data set, you use a KH, Kaggle Hub dot load data set. Yes. And then you pass in the link to the data set. But this link to the data set that I pass in, right? This first part of it, right, is not needed because load dataset already knows, since you are using Cargo Hub already knows that it is going to go and check in cargo.com. And since you are loading datasets, it also knows it has to check in the datasets path. So what you really need to do is the path to the dataset, which is what I copied here, this person's name and the name of dataset. Okay. That's how you run that. When you do this, load data set is going to, okay, I think I'm using the wrong, I always confuse this. So I need to check if I did the right thing. Uh, oh yeah, so I have, um, okay, so this should actually be download, not load, um, dataset download, not load. Load is for after you have already downloaded it. Okay, so this is the correct thing. So pardon me. Um, when you are reading it the from the internet, you use datasets download. But if you have already downloaded it before and you want to read it from your local computer, then you use load dataset. So dataset download is going to download this dataset. Then it's going to give you this data here is the path to where it downloaded it. If you look at it, so you see that it has downloaded it into this location, right? This location is actually here if you pay attention, but you will not see it from here. You have to go up and there's a cache folder, but we will not see the cache folder. Or if you click on this eye here, right, it will open, it will allow you to see hidden files and folders. Um, so cargo. Okay, root folder. Okay, it's in the root folder. So in this root cache, but I'm not saying you should go check all of this though. I'm just showing you where it is. You actually see that it has downloaded it into this folder, right? And you even see that there is the file is actually here, but it's kind of I'm just kind of showing you where this goes, but don't um you don't need to worry yourself about this. Let's go back to our where we have our stuff. So open. All right. Now, data is a path to where you can pull the data, but for you to load it, you now need to basically use this data path, okay, to get the data from it. So how you do that is you use a pandas data frame, okay? Um, let me show you again. Let's go back up. If you go, sorry, yeah, go to root, cache, cargo hub, data sets, the name of the owner, the name of data set, versions 1. So it gives you the full path to this. And you see that in here you have my file 1.csv. And I could even double click on it and you will see the data set here. Okay, so to now pull it into my Jupyter notebook so that I can do stuff with it, I need to use path. So okay, let's just have this, that's okay. You import um, from pathlib, import path. So path allows you to manipulate paths. So you can just say data path, data set path equals um, so this is not actually the data, this is the data path. Okay, maybe we should call this data set path. Because it has already downloaded it before, it's not going to download again. It's already downloaded here. So data set path. Okay. So data set file. So the data set file is going to be taking the data set path. So if you look at it, remember the data set path is going to take you all the way to this. As we have printed it, you see, okay, the second time we downloaded it is now pulling from the cache. So irrespective of that, the first time it downloaded it and it has it here, right? But the second time it is now taking it from the cache, which is in cargo here, cargo input. Um, whichever one is the case, it will still take you there. So now you find that all you need to do is to append the file name, right? So the file name is my file1.csv. Assuming I had not opened this file window, you can still get the file name from here. This is the file name, which you can actually just select and copy. Okay. And then you put it here. So that's the dataset file. Okay. Now you use pandas. So you use pandas to create a data frame. You can create a data frame. Remember, this file is a CSV file. So you will use read CSV and you pass in the dataset file name. And you can just print pandas, you print the data frame. So you now see that this data frame, which of course we had opened the file here, you have now read it into a pandas data frame. Okay. So I'm doing a lot of stuff here, but I hope you will be able to maybe later on rewatch and practice. This is not really a pandas class, but I'm just trying to do a bit of demo on how you can do data cleaning and pre-processing. Now, if you compare what is here with what I've loaded, you see it's the same thing. The only difference is that here, pandas reads blank cells like this one. It reads them and gives them none. So this none means that pandas did not see any value. These are the missing values. I'm now going to close this. So we now have a data frame. Some things you can do. So look at it. First of all, the rank is good. Well, you see that this rank number 7, okay, is not very correct. So what we can do with rank is, let's talk about data cleaning strategy. So the data cleaning strategy would be something like this. Okay. Data cleaning strategy will be something like this. For the rank, what does rank represent? Rank represents the position of the person or of the tour, not the person, because some people have multiple tours, right? Some artists have multiple tours. So it basically just represents the the current position. So is that something you want to train your model on? Well, okay, maybe, maybe not. But that's okay. You don't even need to worry about data cleaning there, except for that one that you have number 7 repeated twice. So in this one, number 7 is repeated. So what you would do is change the second one to 8. Okay, that's for rank. Number 2. So the second is the peak, and all-time peak, right? So you have peak and all-time peak. So what do I want to do with peak and all-time peak? The peak and all-time peak is kind of like the peak ranking of this particular tour. So that's why this one has 1. This one has 1, 2. Maybe there was a time when this particular tour was number 1, but it was overtaken by this, right? And then this one, there's a time when this one also was number 1 and it was overtaken. Okay. So while the all-time peak is on all-time charts, right? So this is number 2, this is number 7, this is number 2, and so on. So this might be in a particular period or year range, and this might be all time. So if I want to do something with this, the first thing is that I need to remove these guys. This is not part of the information. This is just so I would write a regular expression. So when you do data cleaning, use a lot of regular expressions, right? Unfortunately, this is not a class for regular expressions, so um I cannot really do that here, but I'll use a few of them. I'll recommend you to go and study regular expressions if you want to understand a little bit about data cleaning, okay, and how regular expressions help you. It's a very powerful tool as a programmer. Uh, that simple things you can, simple ways you can use to do them. So this possibly, let me say possibly because I don't know, possibly represents the highest ranking ever achieved by this store. Um, so pick, um, this is just my assumption, but you can go check it out maybe within a certain time frame, right? While all-time peak is all time. So if you want to clean, so the strategy for this is remove the bracketed numbers as those are not part of, they're not part of it, right? Okay, number three. So we now have these currency fields. You have the actual gross, adjusted gross with all of these things here. Okay. So for actual gross and adjusted gross, those are currency. Okay. So you would want to turn them into numbers, remove the commas, remove the dollars, because you want actual numbers, right? You want numbers, not those symbols. So for actual gross and adjusted gross, what you would want is remove commas and currency symbol, right? So that they are numeric. If you look at this other one here, you also see that there's a reference here as well. Okay, so you may want to also remove references. In other words, just remove anything that is not a number. Okay, that applies to these two. Then, um, for then there is okay. Let's just talk about data cleaning first. There are other things I'll talk about later on, like feature engineering and so on. For an artist's tour title, year, and shows, the average gross you also is numeric is so let me add that average gross, adjusted gross, and actual gross, adjusted gross, and average gross. Those are all currencies. Okay. So the years you see that these are numbers, but with this dash in between them. You may also want to do something with this, right? We'll talk about feature engineering later on. So with all of this, okay, let's do a few things. Let's just look at what we can do with these three. I can leave the rest for us to do as an exercise. So, step one, for rank, we'll keep rank as it is. So I'm not going to do anything. Okay, step one, rank. Replace 7 with 8. Now, what's the best way to do that? That's another thing. When you are doing data cleaning, you need to think about it a little bit. All right. I can't just do what this AI is suggesting and say just replace 7 with 8. Which of the sevens, which of the two sevens do I replace? So for me, a better way would be I assume that this is already ordered. So all I need to do is I take the index, which is properly ordered, and add 1 to it. So I could do something like this. df rank equals dot index. So I'll take the index. So if you ask what is the index, let me show you This requires a bit of knowledge of pandas, so I would advise you to go learn a bit of pandas. But let's look at the index. The index is a range index. It starts from 0 and stops at 20, step 1. If I convert it to a list, which is really what, if I convert it to a Python list, you see it will give me a list of numbers. And this list of numbers from 0 to 19 corresponds to this 0 to 19 that you have on this first column. So if I take this list and then you do a list comprehension, you can add one to each value. So you can do a list of df index, right? Of idx plus 1 for idx in df index. So this is a Python thing. And if you are familiar with Python, you should understand this. This now gives me numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which corresponds all the way to 20, which corresponds to the rank, the correct rank. So I can then take this, right? Even if I don't convert it to a list, it's already a list comprehension, so it's already a list. I can then take this and then just the data frame rank equals that. Simple. So this will do it, but it will not tell me what it is. So if I want to see what it is, I can still run the data frame again. And you can now see that I have a rank that is clean. That number 7 has become number 8. This is a cleaner way. This is a cleaner way of doing it. This is a cleaner way of doing it than to say, let me search for a specific 7 and replace it. The reason why I was able to reason it out this way or think about it this way is because I understand what that column does, right? So one thing with data cleaning is you cannot clean data when you don't understand what that data is for or what it means. Okay. So like I said, for example, in a school thing, you cannot say, okay, let's replace the ages. People for students that did not provide their age. What do you do? Do you replace it with the average age? You need to understand what you are using that data for and so on. Okay, so that handles the step 1, which is the rank. We basically have clean rank. Now for this one, we could, first of all, let's remove all of this, okay? So for step 2, I would say replace references, bracketed references. Okay, so you use regular expression, like I said. So in a regular expression, you could do something like this, df, you specify this is um what let's see, what is it again? Peak. So peak, okay, equals yeah, so let's take this and I'll explain this so that we can understand. df.peak gives you everything in that column. So let me prove it here. So if you print this, it gives you just that column. df peak just gives you only that column. Okay. Remember, df is a data frame that contains everything. So df contains everything, right? It's the whole data frame. Now, when you narrow it down to and you subscript it with peak, okay, that will give you just the peak column. Okay. So in this peak column, now it is giving you this peak as a series object. So it is not a if you put type here, Python will tell you that it's a series object. It's a pandas or called a series. It's a series object. So you cannot manipulate it like a string. But what you can do is that when you use it .str, then it gives you a string representation. So it becomes an accessor that is built into pandas that allows you to access the elements of that particular series as strings. So with that, we can then access and do stuff with the string. So for example, replace. We can now use string methods. String method allows you to do regular expression replacement. It to apply whatever you want to do with each of the elements. So I now say replace, and that's what it's doing here. So kind of explaining this. This thing here is what we call a regular expression. Okay. There's a slash, this. It will take a bit of time for me to try to explain this, but let me just do it quickly. When you see this, that's why I say go and study regular expression. This thing here, um, so we use, there are a lot of books on regular expressions, so I would recommend it. Here, right, the regular expression means any number, right? Um, Rather, let me put it this way. This regular expression, in regular expression, the slash D means, let me break it down. I know we're running out of time. Slash D means a number, right? Any number. In other words, 0 to 9. Slash D means the same thing as 0 to 9. Now, plus means one or more. So slash D plus means one or more of any number, right? So this slash D in here plus means it needs to match at least a number, any number, one or more of any number. So it could match 0, it could match 00, it could match 01, it could match 45, right? It could match 8923. Any sequence of numbers that is at least length of 1. That's what the slash D plus does. Okay. Now, um, this bracket open and bracket close has a special meaning in regular expression. So you cannot just write um one or more number. So basically, what we are trying to match is something like this: 0, um, 23. Something like that. You can see that things like that here. You have numbers, but you also have letters, by the way. So that's interesting. But the one we are trying to match is one or more numbers, right, that are um um wrapped around these brackets. So that's what this slash means. Now, we could have just said slash D, right? We could have just said something like this, slash, sorry, bracket, slash D plus. Okay. But this bracket has a special meaning in regular expressions. So if you don't want the regular expression engine to translate or interpret this as something else, you have to put the backslash. So the backslash is what we call an escape character. And it basically means take this as a whole unit. It's going to take this as a whole unit, but the backslash will say, don't interpret this bracket open as a special thing. Just interpret it as an actual literal bracket open. Same thing with this one. Interpret this bracket close as a literal bracket close. The backslash says it's an escape character. That's how it works in regular expressions. Then this one is what I had already explained. So this combination now says that anything that is inside opening and closing square brackets, right? Any number of numbers, any number of digits, right? You will match it. And that's what this is saying. So if it matches anything, if it matches this regular expression, which means match any number of any length of digits inside opening or closing brackets, opening and closing brackets, then if it matches it, replace it with an empty string. In other words, replace it with nothing. In other words, delete it. That's what this regular expression string replace does. So regex is true. It's just telling Python that, or pandas, that this replace method should consider this thing as a regular expression and not a literal string. So this will replace pick. Anything, any way it sees this thing, right? It will replace it with nothing. Same thing with all-time pick. So it does the same thing. So if I run this now, you're going to see that all of those are gone, except this one. So why is this one not gone? Because this is not a number. This is a letter. an alphabet, an alphabetic character. So we would have to make our regular expression. There are two ways. I could do another, I could chain the replace as well, and I'll do the same thing, right? R means regular expression. And then yeah, but this would not be nice. So instead, what we'll say is incorporate letters into this. So the way to incorporate letters is what we call a character class. Um, yeah, so the best way to use a character class in regular expression is the actual opening and closing brackets, which we were saying, let's not do opening and closing brackets. Hmm. Let me think if there's another easier way to do this. But the proper thing, yeah, okay, so we can do another one. We can do another one. We can still do another one. So we'll chain it again the same way because replace is going to still give you back the series. So what you need to do is you still chain a string and replace again. But this time around, we will specify letters instead of numbers. So letters, we can use a character class. It should be R. We use a character class. I'm not going to talk about character classes, but um, this is how a character class looks like. Ideally, the best way would have been if I do A to Z, A to Z, 0 to 9, that will also cover for numbers. Okay. This actually also covers this because 0 to 9 also covers the slash T. This is a bit more advanced regular expression stuff, but just take it that it does that. I would really advise you to go and, read about it because regular expressions are very powerful and they will come in handy when you are doing data cleaning. So you see that first one that we had a C on line 14, right, or rank 15 next to 2, we have removed that C now. It is gone. But yeah, so we still have numbers here. So that is now the next thing we will do with the numeric fields. So the numeric fields, we can do the same thing. So let's take it one by one. So we'll start with the actual gross. So you interestingly, you see this funny character here is because there is a space here, right? But this space is not a normal space, right? It's not a normal space. It's a special kind of character space. That's what this thing means, A0, right? So we use that. Um, Sometimes you may want to do a better job of cleaning it. Okay, so let's accept this. Now, let me see if I can explain this. So we still have this, which removes the, it does basically the same thing as this. It removes references, but I'm going to modify it so that it removes both numeric and it's not just numeric references. This was just numeric references, but I want to remove both alphabetic and numeric references. So that's what this does. To explain this, A to Z means any character that is in the range of A to Z, small letter A to small letter Z. While this A to Z uppercase means any character that is in the range of uppercase A to uppercase Z. Then 0 to 9 means any character that is in the range of um 0 to 9. This is actually a short form of saying any character that is in this range, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, right? That's what, um, that's what, that is the expansion of that A to Z, right? That's the expansion of it. Now, it doesn't make sense to each time I want to say, okay, any of these characters, this bracket, take notes, this bracket here doesn't have a slash. So this bracket is going to be interpreted as a special symbol in regular expressions. And in regular expression, the bracket means any of these characters. It will match any of these characters. Okay. So everything in between these two brackets, if it matches any of them, that's what this means. But instead of us writing all of the characters out, all the characters from A to Z, We just use the dash. That's that's what this, so it means anything from A to Z, then anything from capital A to capital Z, and any number from 0 to 9. This is the same thing as also writing 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is the same thing as the slash D that we had before, which is a character class. It's just two different ways of writing the same thing. That regular expression. I will not try to explain it anymore. Now, this is really nice because here it's also trying to replace the so the first thing we do is first of all replace the um these annotations or references. That's what this does. It says any alphabet, lowercase, uppercase, or number, any length of it, right? Remember, plus means one or more. And then between these brackets, but remember this bracket is escaped, so it is a literal bracket. So this is going to match this. So when you replace that, then the next thing is you will replace the dollar symbol and the comma. The dollar symbol also has a special meaning in regular expression. That's why you have to escape it. But if you want it to be interpreted as a literal dollar, so that's that. And then the comma. The comma actually doesn't have a meaning in regular expression, but that's okay. So this will replace all of that. We can now do the same thing for the adjusted gross. So this adjusted gross has a whole bunch of characters. If you're not careful, you will actually miss this, right? So I'm just going to copy and paste, but copy and paste will not even work because these spaces are not regular spaces, they are the XAO spaces, which will have to essentially replace these ones with XAO spaces all through. This is not a very nice way of doing it, but there are better ways. It's just that we don't have a lot of time. So yeah, so we'll still do this same thing. We'll still use the same replacement algorithm here. So I'm just going to copy and paste. If you're writing code, you do a better job than this, right? So with this now, I can print the data frame again. All right, so I have a key error here. It's essentially telling me that um I have missed the spelling or I have missed something. So this is going to be a challenge. So there may be other ways to do this. One other way to do this would be to um, replace the column and rewrite the column properly, right? Um, this probably should have been the first thing we should have done, try to rewrite the column properly. Yeah, so I'm still having key error because this is not matching exactly the columns. So one thing we could do is use the column index. Okay. So what I'll do here is um uh you could actually use a column index here. So let me just use the column index. If you look at the column index, this is 0, 1, 2, 3, 4. So that's 4. It would still work, right? Um okay, so we have this is not correct. Maybe we need to escape the bracket. One way To go forward here is replace let's replace all the column names. So you could do column names, right? Um, so you see you have the column names here. It's an index with column names. So instead of me trying to figure it out, I can just extract it here. So for example, column names 0, 1, 2, 3, 4, which is what I was trying to do before, is this adjusted XAO. So it is actually the one in between that is this, right? So maybe I can still use that, but I'll rather just go ahead with the column names. We could also clean the column names as well, right? But let's just go ahead with this. All right. So this is another way if you're having that kind of challenge. So you can now see that I have for the actual gross, I have also replaced. For the adjusted gross, I have replaced. So this is now a clean number. So this is just how you do data cleaning. Um, Now we can still do the same thing with average gross. Maybe I should do average gross as well. Um, we could just say average gross. I think average gross is the same thing. DF. Yeah, so average gross, you can now see it is cleaned up here. Now, let's talk about the nans. Nans are not a number. So not a number. In this case, it means that the nothing was supplied. So we have to ask ourselves, what should we do? Should we remove the row? Should we replace it with the peak value? If you look at this, at the very least, I could say that the peak value, there are two things. The peak value may not be useful, so we'll remove the whole column. But if you want to retain it, you could say, okay, since peak value is the highest ranking it has attained, I don't have any other information on ranking except for the current ranking. So maybe what I just do is I just use the current ranking. Okay. So the way to do that is let's say step 3, um, replace missing values. Okay. So we'll do something like I'm going back to check what my strategy was. So we've done all three anyway. So the fourth one would be replacing missing values. So this is actually step 3. Currency fields, clean currency fields. Okay, so replace missing values. So let's say step 4, replace missing values. So it's not too difficult. We can just say df the ones that have missing values are the peak, right? So we will not do fill now. Um, so we specify what we are filling it with. Fill now means wherever you have a nan, fill it with something. Well, what do you fill it with? You can fill it with another column. So you just specify the column you want to fill it with. In this case, it's the rank I want to fill it with. So same thing with all-time peak. We can still, even though all-time peak is not necessarily in the same scale as peak, but we'll still go ahead and do it, right? Um, so all-time peak fill now again fill it with the value from the rank. Okay. And then let's look at the data frame again. So you now see that, yeah, so for those ones that were null, I have now filled them with the actual value. right? But the ones that are not null, they will retain their original values. So this is kind of what you do with data cleaning. There's a whole lot more. After this, you still have to do data pre-processing, right? So we looked at retrieve, filter, and just fixing stuff, inconsistent text. So at least we have seen examples of that. Unfortunately, this is not a class on data pandas. So we'll have to continue. Okay. Now, when you have done that, right, the next thing is to do training. Okay. So let's talk a little bit about training. Um, when you are training, right, you are teaching the model to identify patterns and make decisions based on the data, right? The same way a human being would do that. So the fundamental goal of training is to adjust the model's internal parameters. So these are called weights and biases, so that it can accurately map input data to desired output. Okay. So this is an iterative process and it involves several key stages. So the first stage is the data input. After you have cleaned the data, you now feed that data into um into what we call a training pipeline, right? So that data you now first of all you will split it, what we call the test train split. Okay. Then so when you do this test train split, you now have a training data. So whenever we talk about data, now we're talking specifically about the training data. That training data, you will transform it into numbers. So remember, transformation should have been done before you do the test train split anyway. But sometimes you can also do it after. But since you are doing everything in bulk, it's better you do it before you split. So you transform the data. That's part of pre-processing anyway. Then, so the data you have right now is just numbers. Okay. You take that number, you split it, training data, validation data, and test data. You take the training data, you will now feed it into the model. You are giving it as a mathematical, this is now where you have the computational part of it. The model will take that data, it will now do some calculations on that data, and it will give you an output. You take that output and you compare it, right? So that process, first of all, that process where the model takes the data that you've given to it as numbers and calculates those calculations and gives you an output. That is forward propagation, right? It makes a prediction. The prediction is its own calculation of what it thinks the output should be based on um, the parameters it has, right? Based on its internal knowledge, which is the parameter. We'll talk about that shortly. Then after the forward propagation, you now have a series of numbers that you will use to compare with what you are expecting the model, what should be the correct value, what we call the true or actual, value, right? So you take those true or actual values and you compare them with what the model has actually calculated. And that comparison is what we call a loss calculation. You're actually doing a calculation and you're calculating how far away the model's prediction is from the true values. That is called a loss calculation. And this loss calculation uses a function called a loss function, right? So this function will calculate the error or discrepancy between the predicted value and the actual value. And you want the loss function or the loss calculation to be the value of the loss to be as low as possible. If the value of the loss is high, it means the model is not doing well. It's far away from what you want it to do. If the value of the loss is low, it means the model is performing well. Then after you have calculated the loss, you now do what we call a backward propagation. So backward propagation is where the model is learning. That's actually where the model learns. How the model learns is that this error or loss that is calculated by the loss function is used to figure out how much each of the model's parameters should be adjusted. So you adjust the model's parameter in order to minimize the loss or the error. So this error signal is back propagated all the way backwards from the output where the prediction is made and where the loss is calculated, all the way back to the input where the original data comes in. And from that output all the way back to the input, there may be multiple layers. It's not just a single layer, right? There may be multiple layers. And in each layer, the parameters or the weights and biases will be adjusted all the way backwards until the entire model is covered, right? So this process of backward propagation, calculating the loss, right? That's backward propagation. Then, so this is actually in two steps. The first step is the backward propagation, where you calculate the loss at each layer. Then the fifth step is the parameter optimization, where we use an optimization algorithm, right, to figure out how much the parameter is actually going to be adjusted based on the loss that's been calculated for that layer, right? And there are different ways to do this. Gradient descent is, like I said, a grandfather of all of them. Gradient descent is based on the principle that when you look at the change in the um, loss contributed by each parameter, right? You now adjust the parameter based on that change, but you adjust it in the opposite direction, the negative direction, right? If the gradient is large, right, you adjust it by a large amount, but in the opposite direction. In other words, you reduce the parameter by a large amount. If the gradient is large and positive, then you reduce the um, parameter value. If the gradient is large and negative, then you increase the parameter value. Of course, if it is a small gradient, then the reduction or increase will also be small. So the goal of this optimization process is to minimize the loss function. In other words, make the loss as small as possible. Of course, if the loss is zero, that means the model is predicting exactly what you want it to predict. So it is not making any mistake. So that is the principle. Now, when the training is complete, what you are going to see is one, you find a model that has learned how to predict based on the data you gave it to learn from. That learned how to predict based on that data, right? So the final result is a trained model. The parameters are optimized to present the patterns and relationships in the training data. Secondly, the model learns to generalize. That's an ideal outcome. You want it to be able to generalize. Generalization means that it you give it data and it trains on that data. Then you give it data that it did not train on, new data it has never seen before, new scenarios, new situations, and it's able to still make predictions that are accurate or close to being accurate, right, on new data, right? So you can make accurate predictions on new unseen data that wasn't part of the training set. Evaluation and testing means that's the third part. After you have trained the model, you can check the model's performance by trying it out on a totally separate data set, what we call a validation or test data set. And it still performs well, it still generalizes well on that new data set or those new data sets that you did not train it on. And that tells you that the model did not just memorize the training data, but it was able to extract generalized or general patterns in the data, which it applies to new data. If it memorizes a training data, it means it did not extract general patterns, right? But rather just kind of saved the pattern you give it to learn. That's called overfitting. And it's always a problem in machine learning. So that's a summary of the method or approach that you would use. Okay, so now let's move on to the actual training. Now let's start with the very basic problem, what we call a linear regression problem with a single variable. So when we say linear regression is a statistical method that you use to draw a straight line to model points in a two-dimensional space. Okay. This is how we want to start the training so that it's easy for everyone to understand. Now, um, if you did a bit of simple linear algebra and mathematics in school, you will understand that, okay, the shortest point between the shortest distance between 2 points is a straight line, right? And we used to use this approach where you can um, model a straight line using a simple function, what we call a straight line function, y equals mx plus c, right? That's what you're seeing here, y equals mx plus c. This is the equation of a straight line, okay? Now, um, typically, if you're doing linear regression, what you're saying essentially is that I can draw a straight line to fit my data. That's a linear regression. I can draw a straight line to fit that data. So the benefit of being able to draw a straight line to fit data is that if you have more data, if you have new data, maybe you have the X value, you can predict the Y value by extending that straight line. Okay? That's linear regression, basically. So let me show an example. Um, let's assume, okay, so I'm going to bring in my XCalibur here because I like using that. Um, I'll find a very good tool for doing linear regressions later on. Okay. Okay. So I start off with a few points, right? So I have a few points. Um, let me represent the points with circles. Circles I have a few. So yeah, so uh, I'm just going to place a few of these points around. So if you look at this, let's say we have 4 points in this. Now, intuitively, if you want to draw a straight line through these 4 points, okay, you would draw a line that looks like this. This is a regression line, right? Now let's look at this regression line and try to understand it so we understand the concept of linear regression. The best line, if you look at it intuitively, if I drew this line like this, you tell me, no, that line doesn't make sense. Does this line make sense? Is it a good line of best fit? You can reply in the chat. What do you think? It isn't. If I place this line here, is it a line of best fit? Is it a good line? It isn't. Why? Intuitively, if you look at this line, it's telling you, no, this line should pass through the points, right? It should pass through the points. So the line that is best fit is the line that is close to these points, right? Now, this line here, is it a line of best fit? Is it a good line? Could I improve on this line? Let me ask. Yes or no? You can respond in the chat. Can I improve on this line? Is this the best line? Okay, so what I would like is, okay, which line do you think would be the best? Is a line that is maybe somewhere in between, right? So intuitively, you have already done linear regression right now. You have done linear regression. You have even trained the model. You now have a model that can predict these 4 points. So you have one, two, or rather these 5 points. You have 1, 2, 3, 4, 5 points. You have these 5 points. Okay. And you can actually yes, so somebody saying a line that missed 2 points at least. But sometimes the baseline is not the one that missed 2 points. Because I could actually draw this line between these 2 points, between this point and between this point, I could draw a line. But is this the baseline? It's not the best line. It doesn't look like the best line. It doesn't look like it represents those points. Okay. So, but if I put this line in between, it doesn't even meet any, well, okay, it's kind of in between. It's basically cutting straight in between all those points, right? We feel is the best line. So we have done linear regression intuitively with our eyes. But how do we now formalize this into a mathematical equation that we can then convert into a computer program that we can use so that we can train a model around it? So when we talk about models, the first thing you need to even understand is that this thing here is a model. So let me tell you, let me show you. This is a model, right? This is a model. This line that we just drew is a model. It's a linear model. It's a very simplistic linear model, but it is a linear model. So I can even dare to tell you that this is a linear model in its most basic form. This line we just drew is a linear model. And what are the data points? These are the data points, right? These are the data points for this linear model. What are we have 5 data points, right? So we have this one, we have this. I can do all of that. So this is data point 1, okay? Data point 2, right? This is data point 2. This is data point 3. This is data point 4. And this is data point 5. So we have 5 data points that we are trying to model, okay? So each of these represents the data, or all of these altogether represent the data. We have 5 data points that represent, or 5 sample points. Another word you can use to represent, to describe is a sample point. So you have 5 sample points. Now, in real life, you are training on millions of data points or millions of samples, not just 5. But here you are doing a linear regression, 5 sample points. Okay, so all right. Now, I need to formalize it in such a way that my model, which is this red line, can, how do I, how did I solve it? I solved it by minimizing the distance. By the time you understand the fact that I solved this thing by minimizing the sum total of the difference. So what is the distance? Let's take these guys out first. Okay, so that I don't get this place crowded. So let me take these guys out. And then we now calculate a distance. So what is this distance? It's the distance from this. Oh, that's not what I wanted to do. I didn't want to move it. It's a distance, okay? It's a distance from here to here, right? If I zoom in, let me zoom in a bit. I thought I could zoom in. Um, okay. I actually thought I could zoom in, but maybe I cannot zoom in. Okay, I can zoom in from here. So let me zoom in so that we can see. Um, you have this distance from this point to what this guy predicts. Because actually, right, if I were to put this on an axis, on a graph, because I'm doing this thing and I'm not doing it on a graph, so it's sort of not very representative. But let's do a graph. Let's do a graph. Later on, I'm going to use matplotlib, or I'm going to show you how we do it with matplotlib, right? But yeah, let's do a graph. So let's now say this is a graph, okay? And this is the y-axis and this is the x-axis. So this is y-axis and this is the x-axis. So we have now formalized it into maths. So each of these points has a value of x and a value of y. So we could say point 1, for example, point 1 has a value of x and a value of y. So you could say the value is x1, y1. Okay, so x1, y1, right? So this is the point 1. And then you also have point 2 as well that has a value of x2, y2, right? And it just continues like that until you have this last point, right? Um, until you have this last point, which is x5, y5. So each point has a value of x and a value of y. So interestingly, this graph here, this model that we are now using to model these 5 points, the models do not actually, the model does not actually give you an exact value, right, for x and y. You can give you an x. So let's take an example. If I were to take the value of x at x4, which is where I am. Okay, x4 is even close. So, but if I wanted to take the value of x at x4, okay, let me use a broken line. So x4 here, right? So this is x4 here, right? Whatever the value of x4 is at this point, I'm not going to bother about it, but whatever the value of x is, right? This is x4 here, right? You see that what the actual value is, what the actual y value is, which is a prediction. The y value is a prediction, okay? So the y value is, you have two y values, by the way. You have the value, the actual y value here, which is y4. Okay, so that's y4. That's the actual value of y, y4, y4, okay. I don't know why it's bringing it up, but whatever. Okay, we'll just go with that. So that's y4. But there's also the predicted value, the value that my model predicts. The value that my model predicts is a bit different from this, right? So let's assume the value that my model predicts. I give it a red color. Okay, so let me move this X3, Y3 away. So my model predicts a value. That value is not exactly equal. The difference between what my model predicts and the actual value, that is the loss. That is the error. For this single data point, right? If you look at my model is predicting a slightly different value from the actual value. And that slightly different value, we normally use y hat. So y hat. So this is y hat 4. Okay, so y hat 4 is the value that my model is predicting for this particular single data point, for this x4. So x4, y4 is a real value, but x4, y hat 4. Y hat 4 is a predicted value. Same thing, you can look at 5 as well. So if I were to do the same thing, right, and you will see that, okay, this time around, what my model is predicting for 5 is a bit much different. Okay, it's much different, far different. Okay, this is what you can see this is 5, right? That's y5. Okay, but what my model is predicting for y5, you see, is much different. You have to extend it up to here, right, and extrapolate it from there. So I would even say, oh, okay, you have to extend it up to this point from the actual y, right? You have to extend it to this point for it to get it. So that is y5, x5 rather. So I hope we get the idea of it, right? We get the idea of the difference between a predicted value and an actual value. So this is x5, this is y5 here, but the model is generalizing and it's a linear model. So this is y hat 5, and you can see that y hat 5 is a lot further away from y5. So the error in y hat 5, or the loss, is much higher. So you can now combine all these losses. So you now see that if I were to draw this now, the loss would be x1 minus x hat, sorry, y1. X is always the same, right? Because x is the input value, the independent variable. The y is what you want to predict. So y hat minus y1, okay? If I wanted to use different colors, well, maybe I could use the blue for this and so on. Or well, let's just use a different color. So loss would be each data point has its own, you have y2 minus, sorry, y hat 2 minus y2. So remember, y hat is the predicted value, while y is the original true correct value, right? So by the time you add all these errors, okay, that gives you the total cost, right, of this. So what we are trying to do is you minimize, you once you are able to minimize this, the total sum of it. But you see that one thing you notice that some of them, like this one, the value of y is lower than the predicted value. The actual value is lower than predicted value. But in this one, the actual value is higher than the predicted value. So if you use this formula I just gave for loss, some of the values will be negative and some will be positive. If I just added the loss, there is something called a summation. Um, well, I'll do that on a separate page. There's something called a summation. Then you would find that if you were to sum these losses, let me represent this sum of losses by just saying sum of losses, right? If you were to sum these losses, just summing only the losses, you have a low value. You wouldn't represent the actual error because the negative values will cancel out the positive values. So that is why if we want the actual sum of the losses, we have to eliminate the sign. And there are two ways to eliminate the sign. You either use the absolute value, right, of the sum. You sum the absolute value of the losses, right, which will give you what we call the mean absolute error or the sum of the absolute error. The sum of the absolute error. Or you can square the losses. Remember, when you square two numbers, you always get a positive. When you square a number, you always get a positive result because minus times minus is plus. So you always get a positive number when you square it. So that is the second way of doing it, right? You square the losses. Okay. So you can have the sum of the losses, right? Or the sum of the absolute value of the losses or the sum of the square of the losses, right? That gives you the total cost, right? So when you add all of this up, it gives you a value. That value will be very large. If this thing is up here, you now see that the things move. Unfortunately, I don't have a dynamic graph to show this, but one of these days, or maybe in the next class, when we're still talking about regression, I will have a dynamic you know, that shows this. But you will see that if I move this curve away from here, you see how the this would change. The position of this would now be up here. So the difference, the loss between y hat 5, y hat 5 will be up here, while y5 will be down here. Okay, so you see that the difference, the loss is so high. Okay, so that is not a good place for it. That's not the line of best fit. Okay, if you were to draw this up and then extend this one up to get to that point. Okay, so you see. So the best fit would be bringing it closer. But remember, it's not only the y hat 5 we are looking at, all the other points too. You see this one for 4, y hat 4. This one for y hat 3, y hat 2. So the line of best fit is actually the line that gives you the best sum of squared loss or sum of absolute value of loss. And it will always land here where the thing is somehow equally distributed on both sides. Because if you put it up here, while this one will be close, right? So the loss for this particular point will be small, but the loss for these other ones will be much larger because they're further apart. See, this one is so large. Okay, so your point of best fit will always be a point that it is distributed equally on both sides somehow. And this is a mathematical formulation that gives you that value, right? So sum of absolute value of loss or sum of square of loss. But because the sum of square of loss will be too high, sometimes we divide it by n, where n is the number of data points. So in this case, you have 5 data points, okay? also the sum of the absolute value of the loss, you divide it by n. So this n, when you divide anything, any sum by the number, you get what? The average or the mean. And this gives you what we now call the mean square error. So this is the mean absolute error, MAE, right? While this is what? The mean square error, MSE. Because in this case, you are squaring the error, while in this case, you are taking the absolute value of the error. This is the cost function. The difference between the cost function and the loss function is simple. The cost function is when you sum, is the loss of the total sum of all the data points, right? That's a cost function. While the loss function is a loss of a single data point, right? So this, I hope, gives you a clear understanding of it. Now let's go to the maths, right? So if we go back to this slide, you will now see that y hat, you can now see why this is y hat, because the y hat is a prediction that is based on this linear equation. And there's something I forgot to mention. Therefore, this, remember this line, this straight line, in linear regression, this straight line is now represented by y equals mx plus c, right? That is the equation of the straight line, and that is the linear model. So take note, linear model equation of a straight line is all the same thing. Y equals mx plus c, where m is the gradient of this line, which is any x, divided minus another x. Sorry, any y minus another y divided by the corresponding x, the first x minus the second x. That is the gradient or the slope of this line. That is m. M is the first parameter. So when we now hear of parameters in training models or neural networks or any kind of model for that matter, not just neural networks, the parameters, those are the things you will adjust. The second parameter is a C. In linear model, it's called an intercept. The equation of a straight line is called an intercept. That is the point at which this line crosses the y-axis, right? This value here, that's the intercept, C. That is the second parameter. So from this linear model, you have two parameters, and the two parameters are what? M and C. Those are the two parameters. Those are the two things you adjust. You don't adjust the X because the X is the data. X represents the input data, right? X represents these data points, the X value of each of them. So for each data point, you have an X value like X5 and you have a Y value like Y5. Okay. So that's the raw data. You cannot change it. But the equation represents this line, which you can change. And you change the line by adjusting M. So if I raise this line high like this, it means what? I'm just adjusting the M only, the slope of this line. I did not change. Of course, the intercept also changes as well. But I can also move this line up and down. When I move this line up and down, M remains constant. I did not change the slope, but I changed the C, which is the intercept. Or in the context of machine learning, that is the bias. Okay. So all of this now results in the linear equation, which the linear equation in linear regression, the linear equation is the linear model. It's basically the model that you use to model the behavior of that data set. Okay. So when you are training a model, you can start off with a random value for M and C, and that can bring the line to anywhere here, right? But as you begin to adjust the M and the C, right? Manual adjustment, right? You now get to a point where the loss is the lowest value, right? And that is the optimal parameter set for that model. And you would say, I have finished training the model. So I just wanted to, let you understand that linear regression, that's what I have explained is intuition of linear regression, right? Linear regression is a statistical model. The model itself is the linear equation, y equals mx plus c. Y hat, of course, refers to the predicted value, while the xi, yi are the actual values, right? I represents any of them, whether it's 1, 2, 3, or 4, or 5, or whatever. Okay. The goal of a linear regression is to minimize the error between the actual y and predicted y hat I, which I've already shown you graphically. So once you are able to minimize this error, like we have seen, that line can then be used for prediction. So what that means is that if I come with a new value of x that I have never seen before, right? Let's say I extend this x line somewhere extremely far, either in the positive direction or in the negative direction. And I now have a new value of x, which is a test value. So it is a value that the model has never seen before, right? And let's call it xq, right? This is a value of x you have not seen yet, x, you know, x9 or whatever. Okay, I can now extrapolate this model because I have a straight line equation. I can continue that straight line. That is the extrapolation there. I can continue this straight line to a point where I am now able to um, predict what this will be. Okay. And that is what it is. So once I am able to do that and get to a point where I can predict this, then it means that the corresponding y that comes from here is the prediction of the model. The model is now predicting that this is supposed to be the value. This is generalization because this X9 was not part of the training data. I did not give it this data when I was training the model. Okay, I didn't give it this data. But now it is able to extrapolate and give me a value of y. This is not y5. This y5 is back here, y5 hat. But it's able to predict this y hat 9, right? Which is even outside of the range of what we use to train it, but it's able to predict it. Okay, that is generalization. So that's a summary of machine learning. Well, as far as this, everything else is just really advanced application of this basic principle, really advanced in multiple dimensions. Once you understand this basic principle of linear regression, right, you understand machine learning. So now let's talk about the next thing. So how do we train the model? So remember we said the error is the difference between the real value of y and the predicted value of y, which is y hat. So the error is yi minus y hat I. The mean square error, like I explained, is the yi minus the y hat I. Y hat I here is now replaced with the linear equation, which is the linear model, which is mxi plus c. And we take this error, we square it, we square each of them because we don't want to lose, we don't want them to cancel each other out, the negative and positive values. So we square each of them, we sum it, this summation sign is summation for each I, for each data point. So this is now a mathematical formulation of what I just showed you, right? So for each data point, you square it, you square this the loss the difference between the true value and the predicted value, and you divide it by n, which is the total samples that you have, and that gives you the cost function. So j is the letter that is used to represent a cost function. The cost function is is a function of m, which is the slope, and c. So remember the slope and c, there's only one value of m and there's only one value of c because there's only one linear model. There's only one single straight line that you use to model all these points. So even though I have n points, a large number of points, but I only need a single line to model it, right? So the model will find the line of best fit There's a method called least square, which is what we just did. Least square is basically is mean square error. You calculate the mean square error. You calculate the smallest mean square error. That's what least means, the least square error. It minimizes the square differences between the observed values, right? If you now take this cost function, because of this squaring, you see that it is a quadratic curve. So this curve here is a quadratic curve that represents a cost function. And as every quadratic curve tells you, especially the one with a negative, where the highest power is negative, right? Where y squared is negative, or x squared rather, the coefficient of x squared is negative. You find that it has a minimum point where the value of the loss, the combined loss or the cost is at the minimum, right? So what you want to do is you want to calculate this value, and the value of M and C that corresponds to this point, that is your optimal parameter set. And that is a model that will do the best prediction. So this is now the mathematical formulation of machine learning. Now, um, the point is this, right? We can use mathematical formula to calculate that because this is a quadratic equation, right? So you can actually use a simple mathematical formula to calculate that. It's easy when there are just two parameters, the M and the C, right? But when you have millions of parameters, you cannot just calculate it. The calculation it uses what we call a normal equation, right? A normal form. But that does not work when you have a large number of parameters. So to do that large number of parameters, we have something we call gradient descent. So gradient descent is what we use to calculate or to find the minimum, the point of minimum loss or minimum cost, right? Um, so this is an optimization process, right? Typically, if you are doing a normal equation, right, you will use a method of minimization, which is to find the gradient and then the point that has a gradient of 0. That is the minimum point. This is straightforward maths. This is the simple maths of it, right? For those who remember those maths, right? If you solve, you do it's a calculus differentiation kind of approach. Because for you to find the gradient is the rate of change of the cost function with respect to m. It's a partial derivative. And then also the rate of change of the cost function with respect to c, which is the second parameter. So it's also a partial derivative. So where those two equals to 0, right? Where there is no more change in the cost, no matter how you adjust, right? That point, that point where del J del M is 0 and del J del C is 0. The value of M and C at that point, this gives you the equation. This is a normal equation, so I would just calculate it normally, right? If these are all the data points. Remember, xi, yi always refers to the data points, right? So I can calculate the gradient at that point using this equation. And I can calculate the intercept, right? At that point. So these are the two parameters. The m, let me use slope so that I don't confuse the gradient of the cost function with the gradient of the model itself, the linear equation. So the gradient of the linear equation, which is m, is a parameter, right? We can call that slope, and c is the intercept. But the gradient of the cost function is different, so please don't confuse that. So this is the equation, and you can use this. This is called a normal equation. So if you want to compute that, you can just use this. This is just taking for each data point, right? You have three x's, three data points. The first point x is 1, y is 2. The second one x is 2, y is 3. The third one x is 4, y is 5. So you take those three and you just slot them into this equation, right? So the summation x, again, remember this equation is using summation xi yi minus summation xi times summation yi over square summation square of xi, or summation xi squared minus square of summation xi, right? So this one is sum of the square. While this one is square of the sum. They are different. In the sum of the square, you first square the numbers, then you add them up. But in the square of the sum, you first add the numbers, then you square the sum. So take note of that. And you divide it by this and by n. So it's actually quite easy to do this calculation if you had a calculator or if you could write it as code. So I'm going to give you this as a task to do this um, and calculate the code. Okay, so now when you are able to slot in these values, you can calculate M and you calculate C. And then you can get the equation that represents a linear model for these three data points. And that equation is y hat equals 1.214x plus 0.19. That is the linear equation. And that is a linear model for this. In this linear model, the parameters are these two numbers, 1.214, which represents the M, and 0.19, which represents the C. So we have solved and we have trained this model. We didn't actually train it by gradient descent. We just trained it by solving, the equation directly. That is called the normal method. Now, let's go to real world training. Real world training. In the real world training, you are going to do a different thing. So we can take this, for example, and I'm going to show you very soon when we get there. We can take this data. Yeah, this is where we calculated it. We just calculated it and then we plotted it. So we have this whole data set. There's a lot of data here, right? And we can still calculate it, right? Using MC. But in real life, if you have a lot more parameters, you cannot use the normal equation, right? Like if it's not just M and C, let's say you have M1, M2, M3, M4, and so on. That's what we call a multivariable linear regression. But let's solve a single linear regression with one variable. I'm going to just pull up a simple, I have this already, so let me just pull this up. So a single value linear equation, a linear regression with normal equation. That's what we just did. And I'm going to share this sheet with everyone. If I run, let me just run this so that you can see. So we have three data points. We have x1 and y2. We have x2 and y3. We have x4 and y5. This actually represents what I showed you here. That's the same one. X is 124, y is 235. Those are three data points, basically. Right? So we use a simple calculation. You calculate sum of x, you calculate sum of y. Then you calculate sum of x squared, which is you square the x's first, right? And then you sum it. Then you have sum of xy. You multiply x by y, then you sum it, okay? Then, of course, you can calculate the square of the sums of x and y. So that gives you sum x, sum y, sum of x squared, and sum of xy. If you go back to the equation, the normal equation, the slope or the first parameter is n times sum of xy minus sum of x times sum of y. So you see that here, n times sum of xy minus sum of x times sum of y, right? Divided by this, divided by n times sum of x squared minus x squared minus square of sum of x, right? N times sum of x squared minus square of the sum of x. So you still see that divided by n times sum of x squared minus square of the sum of x. So sum of x raised to power 2. That gives you m. And then the same thing for c. If you check c, you see that c is y, which is a predicted value, minus, sorry, the actual value, the real value, or the true value, minus the m parameter, which you have already calculated, times the sum of x divided by n. So that was a very simple one. So you see it is sum of y minus m times sum of x divided by n. So that gives you c. And by the time you plot this, you have yeah, so this is calculating m and c. So when you have calculated m and c, you now already have the equation. The m and c gives you the equation. So you can now predict by just saying m times x, y equals mx plus c, basically. So that's the linear equation, the linear model for every xi, right? So we now plot it. So when you look at all of this, it is going to give you the summations, and then it's going to give you the predictions. So you can now see the blue line is the fitted line, that's a linear model, while the red dots are the original data points. So this is a simple linear regression with normal equation. We are now using an equation. We're now using gradient descent. I'm going to talk about gradient descent later on, but I'm going to share now. We have a single variable linear regression with gradient descent. So let's talk a little bit about gradient descent. So this is the hands-on for single variable. Let's just quickly talk about gradient descent. So what is gradient descent? Gradient descent is basically, say, a method for you to solve and find the optimal point without using a mathematical equation. Well, without using the normal equation, we still use a bit of mathematics as well. But the normal equation is going to be very, very complex and very, very complicated. Once the number of parameters increase, it is not scalable. So all of the machine learning researchers came up with this better approach, which we call gradient descent. So gradient descent is based on the principle that if you look at the cost function, this equation you are seeing here is equation of the cost function of a linear regression. Basically, this is equation of a mean square error. Remember, it's squared, so it's a quadratic equation. And that quadratic equation is saying that if you're at the bottom of this quadratic curve, that is where the gradient is the lowest, right? And therefore, that is where you have the best line of best fit, okay? Above here, the value, by the way, this equation is not the linear model itself, please. Remember, the linear model is a straight line. This equation is, you are plotting the difference between the predicted value and the actual value. That's what you are plotting here. So here is, in other words, you are plotting the error or the cost. So here is where the cost is the smallest, when the line is fitting the points perfectly, right? But here is where the line is far away from the point. So you see that the y value, which is a cost or the error, is very large, right? Both on this side where the your parameters have gone to negative, or on this side where your parameters have gone positive, right? The value of the cost here is also very large. But here, the value of the cost is very low and close to zero. So gradient descent is now an algorithm that is used to find this minimum function. And I'm going to explain, I'm going to take some time, and I crave your indulgence to take a bit of extra time because we have lost time already. But I want us to get this done so that you can also finish your task as well. The gradient descent is a method that you use to find this minimum point, right? So what happens is you have the cost function, which I've explained already. The cost function measures the error between the predicted value and the actual value. If you plot the cost function at different parameter values, right, you now have this curve. So what gradient descent does is it actually checks. If you look at this curve intuitively, you see that where at this point of the minimum cost, where you want your model to be, the gradient is zero or very low. But at this point, the gradient is very high. You can actually calculate the gradient. The gradient is a measure of this slope at each point. Here, the slope is this. The gradient is, I don't know how to explain this but let's see if I can explain gradient quickly. So this is gradient, right? If you draw a line like this, right, you are going to take, let's assume this is a line, right? And then we are taking the x component of this line. We take the x component of this line, right? And then you take the y, sorry, that's the y component, and then you take the x component. Okay. And let's say the x component, the y component, yeah, you just call it y, right? This is the y component, just call it y. And this is the x component, we just call it x. Okay. So the gradient of this line is y over x, basically. Now, this is not the same as y and x that we use as the data values. So let me back up in order to minimize confusion. And let me not use y and x in this context. I'll need to come up with something else. But typically in mathematics, we use y and x, okay? But yeah, yeah, let me use a different thing. Let me use dy and dx, which is really what it is anyway. So yes, let's call this dy, right? Which is dy, the change in y. And let's call this dx, which is the change in x. This is actually a d, so I don't know what it looks like to you, but this is actually a d. So the gradient is dy, right? Um, dy, right? Divided by dx, right? That is the gradient. So at least this is different from y and x. So dy is the distance, let's just call it distance, even though it's actually a difference. It's the difference between the y value up here and the y value down here. That's dy. And then dx is also the difference between the x value, at this point and the x value at this point. So that distance or difference in y divided by difference in x, that's the gradient. So you can call it g for gradient or grad, right? So this is a gradient of any function. Now, when you apply it here, right? So when you see a line like this line, this gradient doesn't actually mean the line itself, but the value of dy divided by dx. So when you take this line here or this line here, you can actually also draw a similar line that you use to calculate the gradient. That line is this line, right? And this line. So you take those two lines together and you still have a dy and a dx here as well, just like you had before. So you have a dx here, and you also have a dy here. So again, the dy is the distance from this point to this point, vertically, that's the y direction. And then this is the x, the distance between this point. So that's the gradient. You can see that the gradient is very large because the y is much longer than the x. But let's now do the gradient when we are closer to this point. You see, when you are closer to this point, the gradient begins to become really small. Because at this point, if you check it, right, the y is small. It's much smaller than the x. The x is much larger, right? The dx is much larger. So this is a smaller gradient because a small value, dy, over a big value, dx, is going to be small. Now, let's look at the ultimate ideal situation where we are now not at this point, right? But we are actually where the gradient is, at the bottom. We are now at the bottom, right? So let's say we are at the bottom of this curve. At the bottom of this curve, let me not even draw it like horizontal. But you can see that by the time you draw it horizontal, the dy is 0. Can you see that? If you can see that, type a yes for me. The dy is 0 at this point, right? So if the dy is 0 at this point, that means the gradient at this point is 0 over anything, and 0 over anything is 0. So at this minimum point, the gradient is 0. So by the time you have trained your model up to this point, then what it means, you see here, the dy here is 0. So you can see that your model has a very low gradient, or the parameter set at that point has a very low gradient. This is dy is very, very close to zero. I can even say approximately zero. It's very close to zero, but the dx here will be pretty large. And the interesting thing you see is that as the dy approaches zero, the dx becomes very large. Okay, so I hope that that gives you some kind of clarity on what gradient means in this context. Now, at this point, we with gradient descent, yes, so up here the gradient is large, right? Up here the gradient is large, down here the gradient is small. But you now see that by the time you cross, by the way, here the gradient is positive. Interestingly, here the gradient is positive because the x difference is positive on the y. But on this side, the gradient becomes negative, right? So you now have negative gradients at that point. So here you have a low gradient. Here you have a gradient that is zero. Here you have a gradient that is very high. At this point, gradient begins to get negative. Why? Because the difference in y is positive, but the difference in x is now negative. So the gradient is now negative. But even though the gradient is negative, right, its value becomes as high on this side as it is on this side. So this observation is what led to the principle of gradient descent, which is saying, for me to now train this model, I would take the parameter, I'll calculate the gradient of the of the loss with respect to this particular parameter. And that gradient of the loss with respect to that parameter is dj. Remember, j is a loss function. Dj over dm, if we're using m, for example. But when we generalize, right, we now use the alphabet omega or w or theta to represent a parameter, all parameters, whether it is m, that is the slope, or c, that is the intercept. In all cases, we can, so whenever you see w or theta, right, it's just a generic symbol for the parameter. So dj dm or dj dw or dj d theta is how much does the cost function j, how much does it change when I change this weight? That is the gradient, and that's the value you are seeing here. So what we are actually plotting here is actually the j. We are actually plotting the j. Sorry, we are plotting j here, and we're plotting m or theta here, right? So what we are now saying is that for where the gradient is large, that means that the effect of this parameter on the cost function is very high. So we can reduce the parameter. And the principle of gradient descent is saying that this is very important, right? It takes steps in the direction of steepest descent, but opposite to the gradient. It takes steps of steepest descent. So gradient descent takes steps in the direction of the steepest descent, right? The direction of the steepest descent is the negative of the gradient. So how does that make sense? Let's go through that again. The direction of the steepest descent. If you look at this thing intuitively, if this is the point where my parameter is currently, right? And I want to reduce, let's say the W and all of the parameters actually are at this point. And you see already the curve is here. You can see that this is very steep. It should go in this direction. In other words, the parameter should go backwards. In other words, I should reduce the value of the parameter. So if I reduce it to this point, at this point, you can now see that the gradient is not as steep. And the parameter is here, basically. If I want to draw this as a circle, right? The parameter is here at this point. So when it is at this point, okay, it still needs to go down, still needs to reduce. So we'll still continue to reduce it further, right? We'll still reduce it further until it gets to this point. At this point, right, what is the value of the gradient? The value of the gradient is basically 0. But if for some reason it overshoots, right, and goes further negative backwards, then at this point, you see that you now have a negative gradient, right? You have a negative gradient here. And your parameter set is at this point. At this point, negative gradient, what does it mean? You will increase the parameter. So it will start going in the increment in the positive direction. That is, you increase it this way. So when you increase it, of course, it will drop down the slope again. So it will keep on going back and forth like that on in smaller amounts until at some point it will settle at this point, and this is where you will say, I have fully trained my model because I have adjusted the parameter. So again, remember what you are adjusting now. You see this thing that says weight. That's what you're adjusting. You're adjusting the parameters. That is the M and the C. There will be multiple M's and there will be multiple C's in the generic application. But of course, in linear regression, there's only two parameters, the M and the C. So this is gradient descent. So gradient descent works by iteratively taking steps in the direction of the steepest descent. The direction of the steepest descent is actually the negative of the gradient, right? To find the lowest point. So you typically use gradient descent when you have a lot of rows and columns that translate to a lot of parameters. Because if you do that, you will get the solution faster than using the normal method. The normal method is what we just did before, where we used a simple mathematical equation. It is not possible. It's almost impossible for you to use the normal method to calculate optimal parameters when the number of parameters is large, like when you have millions of parameters. So that is gradient descent. Okay, so all of this is basically just verbalization of what I have explained. The gradient descent, the goal is to minimize cost function, right? Which represents the error in the model's prediction. You start with an initial guess. So you can ask this question, okay, what value do we start with for the parameters? We start with an initial guess, right, for the model's parameters. So you can start with zeros, even though it's not um, I don't really recommend starting with zeros. You start with random numbers, okay? Then you now calculate the gradient. When you calculate the gradient, okay, the algorithm at each step will now calculate the gradient. You calculate first of all the loss, which is the mean square error, the error, and then from the error, it will now calculate the gradient, right? And then after calculating the gradient, it will now update the parameter based on the gradient in the opposite direction to the sign of the gradient. And you continue to loop this process. So let's now see how we'll do it with a linear model. So you start off with a linear equation, which is a linear model, right? Y hat equals mx plus c. You now pick, and you have data points x, y, I, y, I. Now, for us to calculate the loss or how bad the guess is, you use a loss or cost function or loss function. In this case, we are using a mean squared error, which I've already explained. So to calculate mean square error is yi, which is the true value for each value, minus the y hat, which is what that model predicts with that original first parameter that you used. Then, of course, this is just an expansion of it. Y hat is mx plus c because you can see here y hat is mx plus c. You sum the square of the errors, you divide it by the total number of data points, and that gives you the cost, right? Now, when you get the cost, you want to minimize this error. So to minimize this error, what do? You find the gradient. You find the gradient. So to find the gradient, right? This is I'm not going to go through all of this because I think I've explained it, but intuitively, gradient descent is, think of it like you are putting a ball in a bowl, right? When you put a small, tiny ball in a bowl, it will always roll to the bottom of the bowl. So the top of the bowl is where you have high potential, high gradient, right? It's always going to go down. The bottom of the bowl is where you have the minimum value, right? low gradient, the minimum loss. So it's always going to roll down to it. So gradient descent basically works that way. Start with initial guess for M and C. In this case, compute the gradient. I'll show you how to do that in code shortly. And then move a small step in the opposite direction. That will reduce the loss. And then you continue to repeat this in a loop until you get to a point of minimal cost function. And by the time you finish that, you have trained your model. So one other thing that is important for us to understand is how do we calculate the gradient? So I'm not going to go through the derivation of the function. Well, I could go through it, right? It's actually not difficult. If you know a little bit of integration and differentiation, right? You remember that our cost function is you see that our cost function, remember, is what? A mean square error is y minus y hat, okay, squared, right? You sum it and then you divide it by n. So if you do a simple differential of this, right, differentiation of this is now going to be 2 of, by the way, you are differentiating it with respect to m, which is one of the, parameters. So you have the 2 will come over here. That's why you're having a 2. And the reason why you have a minus is because this yi here, the y hat I, is actually mx plus c. So mx plus c, since m is inside here and it is minus it, so you have minus m, right? It's just going to be minus m. And that minus m is what gives the negative sign here, right? So that's just kind of giving you a way pointer for those who know a bit of the maths. But if you don't know a bit all of that maths, don't worry about it. This is just the equation that you would use, right? Sorry, I made a mistake. It's minus x, not minus m, because m is the variable that you are differentiating against. So it's the x that comes out. So the minus x. So that's why you now get the minus affecting the 2, and then the x remains here, right? So I think I'll still do this again, um, some other time, or maybe I can even do it now. Let me do it again. So we have summation of y minus y hat. So y hat is mx plus c, right? Pardon my writing. I'm using a mouse. And yeah, you square this difference, but divided by n. So if you look at this, the 2 comes down this way. So you have the 2, and then this remains, summation still remains, and then the y will still remain, right? What we call product rule, the y minus y hat will still remain. But then you now go in and differentiate this again, which is minus mx minus c. So the minus mx is what gives you the minus x. So you have a minus x here somewhere to multiply this, right? The c goes away and divided by n. So this minus x here, the minus comes out here. You have minus 2 over n. And then the x stays inside the summation sign. So that's the xi into yi minus y hat I. If you do the same thing for with respect to c, you find that with respect to c, this goes away. This is minus 1. So there's no x here. It's just a minus 1 here, right? And then this minus 1 just comes out here. So you have the minus 2 over n times yi minus y hat I. So I hope for the benefit of those who wanted to understand that. But again, if you don't understand it, that's okay. So this is the 2 equations that you use to calculate the gradient. This is gradient of cost function with respect to m to calculate the gradient of m. And then this is a gradient of cost function with respect to c for you to calculate gradient of c. And that's all. Once you calculate these 2 gradients, you now plug it back into the update. The next step is the update. You want to update the weights. So for you to update the weights, this is the part where you update the weights or the parameters. Remember, you update in the direction opposite to the gradient. That's why you have this negative sign here. Negative sign is saying the gradient is del J del M, right? You update it in the negative, that's why you use negative sign in the opposite direction. Same thing with the gradient for C. So it is, you now change M to become M minus the gradient, the big gradient. Now there is a factor here. That factor is called the learning rate. So when you hear of learning rate, the essence of the learning rate is to kind of filter the gradient. You cannot use the entire gradient on top or to modify the parameters, right? The model will just blow up. So we use a learning rate to kind of moderate it. And the learning rate is very, very key. It's one of the hyperparameters that matters a lot when you're training models. So you even see the equation here. So that's how you train this model. Now, we'll talk about multivariable linear regression later on, but I can show you this, right? The multivariable linear regression is just the same as a regular linear regression, except that instead of having one X, you have multiple X's, right? And instead of having one M, you have multiple M's. So here, instead of using M, we are using beta 1, beta 2, beta N. These are just, again, parameters. And then you have beta 0. The C that we were using to represent the constant or the constant or the intercept is now a beta 0, just to unify it, right? That is multivariable linear regression. So in multivariable linear regression, it's still the same thing. You are going to still calculate gradient and update each parameter based on the gradient that you calculate. And it's the same equation, the same formula for calculating. I'm going to show you how to do that. Um, there is the vectorization aspect, but I'm not going to go into all of these complex ones. We'll talk about this when we meet next week, right? Multivariable linear regression with a vectorized version. But we're going to do the very simple one. So let's do a very simple one so that you can use that approach. It is this same principle, right? So let's start. I already have it here, okay? But I'm going to do a fresh um, I'm going to do a fresh one so that you can follow me step by step. And I can tell you I'll be done in just a few minutes. So let's start. So let's say I'll be done in a few minutes. So we let's have a single linear regression. And I'm going to start with very simple data, right? The data is not much. You can see the equation here. This is the important equation for the gradient, but you also need to remember the equation for the cost function. So for single linear regression, I'm going to still take this data from the multiple linear regression, but I'm going to only take one value. So let's assume you have these values for X. And yeah, okay, so this is single variable linear regression. This actually has both. So you have two sets of values, the X and the Y. Okay. So again, I'm just going to do this to explain it. The tools we will use, the libraries we'll use pandas. We can use pandas, but we'll use NumPy, import NumPy, NumPy. Remember I talked about NumPy yesterday. And we'll also import matplotlib so that I can plot graphs, right? And it will be easy to see the graphs that I plot. Right. So this is the X and the Y values. And I put them in NumPy arrays so that it's easy for us to manipulate them. Okay, now so for single variable linear regression, remember I said the first step is let's even plot, right? So the first thing is we'll do a scatter and just to plot the X and the Y. So we'll just plot the X and the Y and you see how it looks like. Okay, so you see this is X and Y. I'm going to put the color is red. Um, okay, so you see X and Y in red. I don't have a model here. This is just the raw data. And you can see it kind of forms a line narrowly. Okay. So the next thing that you would, want to do is let's have a model, you know, our linear regression model that we want to use, right? So we'll start off with just that basic linear regression model. So I'm going to do that now. Um, it's a simple mathematical model, y equals mx plus c. Okay. But we mx, okay, so m times x. Okay. Nice, isn't it? Um, let me rewrite the y as small y, even though technically it should be uppercase, but let's just call it x and y. Sorry, y and x and y. So yeah, so we have x and y. Now we don't know m and we don't know c. So the rule says step one, you have to assume values um for step one, right? Start initialize m and c. Okay, so I initialize m and c. I can just choose any values I like. Maybe m equals 0.3, right? And c equals 0.4. Now I can actually plot this now. I now have y equals m um, x plus c. So let's say y hat. Remember, y hat is a predictions. Okay. Um, m times x plus c. I don't know why this is failing because I have actually run this. Okay, maybe I didn't run it. Okay, so I've run m and c now. So y hat is now your prediction. I can now plot the prediction. So to plot the prediction, I can just plot. Let's plot a simple is we color, and then we also plot the original scatter, the original x and y, which is the original thing. So you now see that you see where the graph is, right? It is not able to, it is not in the best position yet. Okay. We can calculate the cost function at this point and say, okay, the cost function, let me make it a function. So cost function. So remember the cost function, we want to calculate cost function based on the actual y and the actual y hat. So remember the cost function is mean square error. So this is very simple to do with NumPy. Y minus y hat squared. So y minus y hat is the error, right? Then we square the error. Then we take the mean of it. Remember, sum over n is mean. So we don't need to do sum. We could have also done np.sum divided by n. But I'll need to figure out the n, which is length of y. But it's easier to just let NumPy handle that. So np.mean. So this gives you a mean square error. Then I can now calculate that and calculate the cost function. I can just say cost function of y and y hat. Remember, I've already calculated y hat before. I calculated y hat, which is this. By the way, y hat, for your information, if you didn't know, is a list of numbers. It's a list, it's an array of numbers, just to be sure. And you may be asking yourself, why, what's this? The y hat is a complete array of all the y's, of all the x's. Remember, you had a bunch of x's here. So each of these x calculates. That's the beauty of NumPy. Remember when we say that NumPy allows you to do parallelized calculations. It calculates all of them at once. I didn't need to look through it to do one by one. I didn't need to look through to do one by one. I just used it as if it's a single variable. I used X as if it's a single variable, right? But the M, this is also broadcasting. The M is only one value, C is only one value. So it knows how to take the M and the C for each of the X and calculate the corresponding Y hat. Okay. So we have Y hat and then we have Y. One way I can make this easier for everyone to understand is I can do a pandas data frame. So let me say import pandas as PD, right? Then I can do a data frame equals that. So you can see the X, the Y, and the Y hat. And I can actually run that. And you will see the values side by side. So for each X, this is a corresponding Y, and this is my Y hat, which the Y hat is far from the Y. You see how big the Y's are, right? Large values, while the Y hats are a bit far from it. So you can see how it is. Now, so the Y hat is an array. So when I do a cost function, the cost function is going to calculate a single value that corresponds to it, and that single value is 410. It's telling me that this model is not doing very well. So what can I do? If I was doing manual linear regression, I would adjust the values, right? So I'll adjust the value of M and C. Those are the parameters. So let me simulate that and say, okay, M equals M minus, let's just take a value, 0.2. I'm not going to actually do this, but and then C equals C minus 0.1. Okay. And then I'll calculate another Y hat again. Y hat equals M times X plus C. Okay. And I can do another plot of it again. So all of these things I am doing, I should have done it in a loop, but I'm doing it one by one because I'm doing it manually, right? And you see that it has adjusted a little bit, but not too well. Okay, so let's move the value a bit more. Let's move the value. Let's even make C positive, right? And we do another Y hat, we plot again, and you can see it's going down. So let's increase the gradient. Instead of reducing the gradient, we increase the gradient. Because we are reducing the gradient is going down. But now increasing the gradient is coming up. Now let's increase the gradient by a large number, maybe by 2. Okay. You can see it's now coming up to where we want it to be. But this is all manual and it's not very useful. So let's now, right? Let's now formalize it. We will now use a loop. So that's where gradient comes, because here I was just using values to update. I wasn't using any gradient. But to now train this model, okay, so this is a formal training loop, irrespective of whatever values I started with, right? Formal training loop. And one thing I want everyone to know is that the training loop is standard. This formal is standard for any training you want to do on any algorithm. It always starts by we'll give you a learning rate. So let's say 0.1. Epochs is the number of times I want to loop, right? I'm not going to redeclare M and C because we already had it. But let's see, we can just start with initial values of M and C. Okay. So the loop itself always has 3 steps. Step 1 is calculate the loss function, the loss, right? So to calculate the loss, you first of all need to calculate Y hat. Okay. So remember, Y hat is MX plus C. Then you calculate the cost function. You calculate the loss using a cost function, which I had already defined the cost function here. As a matter of fact, I could even decide I don't need to have a whole function to do this, right? You probably don't really need a whole function because it's a single one-line thing. So let's just do it so that it's easy for you to understand. So you calculate the cost. So this is calculate prediction, predict value, calculate cost. When you calculate the cost, one thing we can do is let us store the losses. I always like to do this, for tracking the losses. We can call it losses or, well, losses is what we use. We use an array so we can keep track of the losses as it changed. So we can now say losses that are penned. So you add this particular cost function. Now you calculate gradient. So for each of them, the M will have a gradient. Remember the equation. for the M gradient. Okay, the equation for the M gradient was, if you look at it again, it is for mean square error though, it is this, right? Um, sorry, that's just the update. It is X times the loss. This is Y minus Y hat, so this is still the loss, right? So it's X times the loss, sum of X times the loss of each, right? Times minus 2 divided by N. So the M is going to be minus 2 times minus 2 times NP dot mean. Yeah. So we'll just go with this, right? NP dot mean is again, divide X times Y minus Y hat. So Y minus Y hat again is the difference per each. And then you multiply. That's a gradient for M. And the gradient for C, this time we don't say dj, dm, dj because the j is common. So we just go with dm and dc. Minus 2 times mean of this. And then you update the parameters, which is the last bit of it. After you calculate the cost, the gradients, right? The j, the m. We don't use the j, we just use the m. That's why you're saying dm and dc. We just improve the parameters. M minus learning rate, which is alpha, times dm. C minus learning rate times dc. That's what you're saying here. And that's it. You can even say, okay, let's just print the loss. Print, epoch is epoch I, right? And loss is cost. We could call it cost or call it loss. Um, it's but when you're referring to the cost function, I'll call it cost function. And this is your training loop. By the time you finish this, right, you will see um you can now plot. So when you finish training, this is the training loop. When you finish training, you can now have a plot. You can plot y, x. You can plot x and y. Sorry, plot scatter. Yeah, you can plot all of that. So this is a training loop. This loop here, and it's as simple as that. We have trained this model. The other thing we can also plot is plot the losses, right? To see how it was changing. And this is it. You have trained your model. This was pretty quick. Okay, so we have loss is none. So there's a problem somewhere. My loss is calculating none. But it's probably because of exploding gradients. So remember we were talking about gradients. It's 1,000 epochs. I'm overtraining it. So let me reduce the number of epochs and use just 10 epochs. This is a simple linear regression, so I don't need that many epochs. So you can see one thing you notice here immediately is that the loss is increasing. It's not reducing. So did I do something wrong? The main problem is what we call exploding gradients. The learning rate, the amount of gradient that I'm applying to update the parameters is too much because the learning rate is too high. So you can see how it is increasing from 410 to 14619 to this. If I plot everything, you see that, first of all, my model is crappy. It's not able to do anything. This is something you need to be very careful about when you are training models. You need to be very careful about exploding gradients. You see that instead of my loss reducing, it's blowing up. So when this kind of thing happens to you, and it might happen to you, what you do is reduce the learning rate. You reduce it by an order of magnitude of 10. So I'm going to reduce it to 0.01 divided by 10. And I run this again. And then let's now see the loss. You can now see the loss is dropping. It didn't blow up. It's dropping. And it has gotten to a certain point. I can now run my plot, and you can see that my graph is now fit into this point, right? And you can see my losses. Um, I need to plot this differently. The losses have also dropped. So with this, we have successfully trained this model. And no matter where you start from, no matter where your starting point, even if I started with an M of 0.3 and a C of 10, it will just start with a very high loss initially. But eventually, it will converge. Well, the loss is very high here. I didn't give it enough epochs, okay? So it didn't do a good job yet. So in this case, what happened was I started with very bad assumptions. Let me even see if the model it's reducing, the loss is reducing. So it is converging, right? This is reducing, so it's converging, but it hasn't reduced to where I want it to be. So what you do in that case is you can use more epochs. If I use 1,000 epochs now and I run this, you now see that it has actually converged to the same 2.9. It took 1,000 epochs, but it has gotten there and it still fits to the same thing. And if you check this one, you also see it fits. This is basically gradient descent, and that's the power of gradient descent. It always converges. So this is single variable. Now let me conclude by just taking you through multivariable. So the only difference is that when you're doing multivariable, you have multiple M's and multiple C's. This is single variable where you have one M and one C. But when we now go to multivariable, um, let me bring it back. When we now go to multivariable, you will see that when you're training with multiple variables, you can now see that the x's are many. We have three x's, x1, x2, x3, and y. It is the same principle you will use, right? The only thing is that for each x, you have an m. So you have m1, m2, m3. And for each, and then you have c, of course. Here it was initialized to zeros, but again, I recommend don't initialize to zeros. Then you have alpha epochs. Then for each m, you use the same equation to calculate the error. To calculate the gradient. But instead of using, for M1, you use X1 times the error or the loss. Okay, and we're tracking the loss. So for each M, you multiply the X by error. So you have three gradients. And then for each M, you also update it the same way. So multivariable is the same as single variable, except that you now have three M's or multiple M's and one C, and then multiple DMs and so on. It's the same thing, right? And then when you come to visualization, plotting the graph, you also see how you can plot it. So there is this multivariable linear regression with vectorization, which I will explain next week. But what I am recommending everyone to do is to use the one where you are calculating each x separately. So that brings us to the end of linear regression with single and multiple variables. Are there any questions? Yes,
No,
go
I
ahead.
don't think.
Blessing, you have a question. Go ahead.
Okay, thank you so much. I got confused by what the DM and the DC represents.
Yeah, so those are gradients. But you remember gradients, right?
Yes, I do.
Okay, so the DM is just a name I am giving to the gradient. That's all. And let me explain it again the way I explained it before. In the yeah, in here, the gradient was calculated as with DJDM. So you understand the DJDM, right? And the DJDC.
Yes,
Yeah,
yes.
so I'm just, instead of writing the full DJDM, right? I'm just writing DM. Do you understand? And then instead of writing the full DJDC, I'm just writing the DC. Do you understand? So it's just the same thing. It's just the notation. I could have decided to write here DJ, DM, right? So you can still do that if that will make it easier for you. Do you understand? So it's just a symbol, but it basically means a gradient. It's just a gradient. The gradient of the cost function with respect to the M parameter. While the
Mm,
DJDC is a gradient of the cost function with respect to the C parameter. Is that
mm,
okay?
yeah, thank you.
Okay. Do you have any other question?
No, but to be clear, so it says the gradient in respect to the m parameter, and the
Yes.
m parameter, what you are saying is the weight, right?
Yes. M
Okay.
parameter is one of the weights. The C parameter is another of the weights. It's
Oh,
just that in linear regression, because the regression model is a straight line, and the M and the C are the parameters of that straight line, right? The M is the slope, and the C is the intercept.
okay. Okay.
Uh-huh.
Thank you.
So, but those are parameters. So you find that basically in machine learning, all parameters are basically coefficient of some kind of equation that is used to characterize that model. So the model, when you hear model, the model is the equation that you use to represent. It's just that some models cannot easily be represented by by a single equation, but rather a system of equations, right? So, for example, in linear regression, the model is the linear equation. In logistic regression, it's still a linear equation, but it's a linear equation with multiple variables, multiple x's, right? And the same thing with multivariable linear equation. It's just an equation, right? Decision trees is no more an equation, but it's more of a logic, um, 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 what I would call a set of rules, right? But those set of rules can still be represented mathematically. In a neural network is essentially a system of linear equations with a nonlinearity introduced. That nonlinearity is called an activation function. But a neural network is a system of equations. It's very difficult to characterize it mathematically, but we now use more intuitive methods to represent neural networks by looking at neurons, layers, and all of those things. But at the depth of it, a neural network is basically a system of linear equations with a non-linearity introduced at certain points. So effectively, when you hear the word model in machine learning, we're actually referring to a mathematical equation, a system of mathematical equations that is used to model the behavior of the data. That's why it's called a model. So I hope that helps.
Yes, thank you.
Okay, so we are very late, but I just had to take this and I apologize. Let me stop the recording.